talking about the holographic universe in terms of variety. So I'm sort of inspired by, I bridge the math and physics. So any math that I'm into is like fiber bundles or sort of very strange F-theory stuff, and algebraic geometry is my thing. So first of all, what in the world was the title? Let me unravel that. So right, algebraic variety, what am I talking about? I'm talking about the zero set of solutions of a system of polynomial equations over the real or complex numbers. Algebraic varieties tend to have graphs that look like this where we're splitting things over different planes. So what is an algebraic curve? Okay, so I just let f of z naught all the way to zn be a homogeneous polynomial, and it's just a zero set over the complex. Oh, right here I'm going over the complex plane. So is every manifold a variety? So in string theory and all these higher branches of physics I'm like researching, above every space is another space. So they're trying to figure out what is a fiber bundle. Can we think about fibers in terms of variety? So I just play in all these intersections, and that's what I'm trying to figure out. So building the connection between holograms and variety. So Wheeler, Archibald Wheeler, I forgot what year, maybe 60s. So he said reality was information. He first of all said reality was geometry, but we find that. Reality is information as in quantum information. And then Susskind said that information is indestructible, so you can never be destroyed. That awful photo of you can never be deleted. You know? So everything is in zeros and ones. So why are we talking about holograms? So a hologram is a 2D scrambled surface that encodes information in a 3D object. So the boundary idea. What are we talking about? This physics on the boundary. So it originates from very, very basic. I don't know, what is this, Cal 3, where they teach you like Stokes and things? Is that what it is? Okay, yeah. So maybe early E&M, like pre-relativistic E&M, they teach you this notion of physics on the boundary. So your giants in string theory took that notion of physics on the boundary and went crazy. So they're saying they came up with this major duality between a certain hyperbolic space and a solution of Einstein's field equation. So hyperbolic space is gnarly. Somebody was talking about it earlier, right? Let's have fun at hyperbolic space. So the shapes are the same size, but I think it's always fun that the boundary is infinitely far from any point in the interior. So ADS spaces is inside, and you're going to have a conformal boundary. Conformal just means angle preserving. So the duality, the other piece, is this conformal field theory bit. So it's just a quantum field theory. It's just a quantum field theory invariant under angle preserving transformations. You know, I mean, you have to say just. This stuff is out there. You know? So that's the other piece of the duality. Anyway, so what is the correspondence? So Maldacena, so he's a giant. He's at the IAS right now. And so he said that ADS space is just a stack of disks, that you can get that the space-time looks like a solid cylinder. The boundary is the space-time for quantum field theory. So he's doing the notions of physics on the boundary again. So these are just some of the equations that are, you know, pretty wild. Anyway, so most importantly, what is he saying? Quantum field, or the conformal field theory is like a hologram. So it's capturing information about the higher dimensional quantum gravity theory. So it's pretty rad that he made the boundary equivalence again in terms of holograms. So what is a duality? Well, again, so it's just this principle where two seemingly different physical systems could be equivalent in a non-trivial way. So you do the transformation, somehow the two theories look the same. So that's how they're going from ADS space to a conformal field theory. So what have we done? It's crazy. So you've equated a theory with gravity in n dimensions to a gravityless theory in n-1 dimensions. So that's that notion on the boundary. Right? Stokes goes from like a contour, closed contour, to like an area. So this like n-1 n kind of thing. What have we done? It's not me. I mean, I'm trying to get there. Right? So what are the implications? This is pretty crazy. So a gravityless theory in n-1 dimensions is going to encode a gravity theory in n dimensions. So how in the world have you done that? Well, I was trying to tie in, maybe it's like a variety notion. Maybe it's some kind of smaller zero set that you've blown up. So they coined, Susskind at Stanford, and I met him, he's awesome, coined the holographic principle that our universe could in fact be just 2D. It can only appear 3D, right? So that we're not really here, that this already happened. And then also, I know, right? And it's encoded on the boundary. Some 2D boundary we're encoded on. It makes sense. It totally makes sense. What is the connection between the holographic principle and algebraic varieties, right? So, So I'm trying to figure out what in the world, I was trying to hit it from the math side since I'm stronger at math, you know? So, well, you gotta know what a blow up is in algebraic geometry first. So what happens is that you have a singularity, any cusp, anything. So, these singular points, they're called blown up to the real projective line. If you Google like blow up, just don't do that. You get weird stuff when you Google that. Anyway, so you have this singular cusp, right? And they call it a singular scheme. Scheme's a funny word. People still don't know what that means. Anyway, so you have this curve that has a point here, and it's neat. They just they unravel the point by replacing that point with a projected by its tangent space. So it's that whole n to n plus 1 thing. And then at the end, so wow, what is it? So I think I'm trying to get there in order to like believe that I think that. The 3D universe is a globe with a 2D hologram. It's pretty rad. And they also call it that we're living in a causal diamond. So yay, thank you.
Wow.